So welcome all. So welcome to Dr. Rajesh Biogenesis CSNet Chemistry Academy. So myself Dr. Rajesh Kumar Povaku, your concerned organic chemistry faculty. So today we are starting a new chapter. So most probably it will be almost all most important for variable competitive entrances such as CSR net, GATE, SET, whatnot, and even you can go for IIT, JAM entrances and even G entrances. So almost all from basics onwards we are discussing organic chemistry, so that it can be helpful for your even chapters also. Okay, even if you are very weak in organic chemistry, especially in your PG standards, whatever PG syllabus you have, and that syllabus connectivity will be there from your basics only. If you know basics clearly, almost all maximum parts will be very easy for you. Okay, so we are going to start with general organic chemistry. Keep it as GOC, general organic chemistry or basic organic chemistry. Almost all maximum basics we are going to discuss here, starting from what is hybridization, how to calculate hybridization of organic as well as inorganic molecules, and what are the shortcuts for hybridations for inorganic molecules. Later we'll see how to calculate number of lone pairs, how to calculate charges, then what is linearity, planarity. So what is hybridations of variable carbon constraints and carboxylic acid derivatives, as well as some selective functional groups. Okay, later on we will see what are electronic displacements, types of fissions. Then we also discuss what is inductive effect, mesomeric effect, hyperconjugation, etc. Okay, so almost all your maximum organic chemistry parts depends on GOC only. Almost all it is a heart of your organic chemistry. If you are familiar with GOC, maximum organic concepts will be in your hands. Okay, after that we will see what is reactant intermediates, what are reaction mechanism, then named reactions, rearrangements, then go for pericyclic reactions, stereochemistry, etc. So that is a sequence, but you people will be very strong in GOC only, because GOC will influence each and every chapter. Suppose if you are learning any IR question or if you are learning any HNMR question, almost all it is depends upon the electronic displacements only. Means how electron densities get influenced by donating group as well as withdrawing group. If you know concepts clearly on this particular things, then automatically maximum 99% of organic chapters are depends on GOC itself. Okay, right. So so first listen, don't write. I will give some introduction, then you listen. See, GOC generally, see, we know according to vital force theory. Just listen, I will give notes, just listen. Vital force theory is saying that organic compounds are prepared from plants and animals only. See, we can plants and animals. With the help of plants and animals, we can prepare organic compounds. Means I want to prepare any organic compounds. According to vital force theory, they are isolated from plants and animals only. But in 1828, Friedrich Euler, he is the first scientist who introduced a synthetic organic compound. That synthetic organic compound is urea. It is prepared by using ammonium cyanate. When ammonium cyanate on heating, simply there is a formation of urea. This is urea preparation. So this is a rearrangement reaction. Rearrangement reaction is a first synthetic reaction. Ammonium cyanate is a rearrangement reaction. It is prepared by Friedrich Euler by heating. It is an inorganic compound. Inorganic compound converts into organic compound. Now these properties are almost all equal to human urea. So it is a first rearrangement reaction. And urea is a monoacidic dibasic in nature. Okay, you need to remember this point. What is monoacidic dibasic in nature? So what it means? Monoacidic dibasic in nature means only one proton can be delivered in tautomerism. Suppose here how many protons are present? 4. Only one hydrogen can migrate from nitrogen to oxygen, not all. So either this hydrogen or this hydrogen, this hydrogen, this hydrogen, overall 4 is there, but 4 cannot involve in tautomerism at a time. Only one hydrogen is involved, that's why it is called monoacidic. Dibasic is nothing but this nitrogen lone pair can be donated as base. So 2 lone pairs are available. That's why it is called dibasic in nature. So urea is monoacidic dibasic in nature. Then what about IUPAC name of urea? IUPAC name of urea is C. Amino methanamide. Amino methanamide. Okay, who proposed first synthetic organic compound? Friedrich Euler in 1828. He was saying that we can prepare a organic compound by heating a inorganic compound. Otherwise, he was saying that yes, we can prepare a synthetic organic compound by taking any other sources. But this theory is saying that, vital force theory is saying that on the time, organic compounds are impossible to prepare in laboratory. They can be prepared only by nature. Nature should give organic compounds. So that's why this theory is finally not exist. Okay. So now after that, many lakhs of organic compounds are introduced, and every year lakhs of organic compounds are synthesized in laboratory. So that's why finally after 3 years this theory is going to be violates. Okay. So that is amino methanamide. It is a rearrangement reaction. Now see, if you see most of the carbons, most of the organic compounds, carbon is in which state here? Excited state. Why it is excited state? Because in order to attain stability, carbon want to attain stability, that's why they undergo excited. So normally what is carbon atomic number? So can I write electronic configuration like this or not? 1s2, 2s2, and this is 2p2. It is a ground state or not? So ground state 2 electrons, and what about here? 2 electrons. It is a ground state electronic configuration 2s2, 2p2. If one of the electron excited here, total how many electrons? 1, 2, 3. So 4 electrons are present. Now this electron combined with hydrogen, here also combined with hydrogen. Then what is the valency of carbon? Valency of carbon is 4. So finally I can say that tetravalency. Is it methane exists in ground state or excited state? Excited state only. It is a ground state configuration. Ground state configuration is mostly belongs to carbene configuration. This is excited state. Excited state configuration where 4 electrons are available in free form. So why they undergo excited state? They undergo excited to attain stability. See, when this electron excited here, you will get 4 electrons. These 4 electrons are valence electrons of carbon. Now these 4 electrons combined with 4 more electrons of hydrogen finally forms tetravalency. So finally 8 electrons are completely stable. That's why methane is exists as gaseous form and it is found to be stable. So your question is, in majority of organic compounds, carbon is in excited state. Why it is in excited state? Why it is in excited state? In order to attain stability, they undergo excited. So final thing is, carbon want to attain stability, that's why it is undergoing excited. And very important thing is, around this carbon I written hydrogens with the same bond length. This hydrogen, this and this. Almost all 4 hydrogens having same bond length or not? They having same bond length. So one bond length is very high, other is very short, like that they are not available. All having equal bond length. So in order to attain equal bond length, carbon undergo hybridization. See, this carbon hydrogen undergoing same bond length, here also bond length is same, here also bond length is same. So bond length around carbon is almost all same for identical atoms because they undergo hybridization. So what is the use of hybridization? It is intermixing. This all 4 orbitals which are combining with this hydrogen, they will first undergo intermixing. So when they undergo intermixing, then all 4 orbitals having equal energy, that equal energy hybrid orbitals combine with hydrogen and forms a hybrid orbitals. Clear? So finally we can say that these 4 atomic orbitals are intermixed together and forms a hybrid orbitals. That 4 hybrid orbitals are equally distributed with same energy. And finally, this carbon, whatever 4 hybrid orbitals are present, 1, 2, 3 and this is 4. That 4 are intermixed hybrid orbital, that's why they are maintaining same bond length. Clear? So what is hybridization? Intermixing of atomic orbitals to give hybrid orbitals. So I am intermixing one s orbital, p orbital, p orbital, p orbital, all I am intermixing and I am giving a similar and equal energetic hybrid orbitals. That hybrid orbitals will give identical bond length. Equal test I am saying. See, one s orbital I am mixing, 3 p orbitals I am mixing, px orbital, py, pz, all I am mixing. So total how many? 4 I am mixing. When you mix 4, that 4 will be hybrid orbitals. Atomic orbitals to Hybrid orbitals is called hybridization. Okay, right. Write one point. According to vital force theory, organic compounds are isolated from plants and animals. Organic compounds are isolated from plants and animals. Next, in 1828, first synthetic organic compound. In 1828, first synthetic organic compound prepared in laboratory by heating ammonium cyanate. By heating ammonium cyanate. By heating ammonium cyanate. Okay, next. The first synthetic organic compound is urea. The first synthetic organic compound is urea, prepared by Friedrich Euler. Friedrich Euler. F-R-I-E-D-R-I-C-H. Friedrich Euler. Okay, so you write this reaction. Then write this. Urea is monoacidic dibasic in nature. IUPAC name is ammonium methanamide. Amino methanamide. Urea is monoacidic dibasic in nature. IUPAC name amino methanamide. Right. In variable organic compounds, carbon is in excited state. In variable organic compounds, carbon is in excited state to attain stability. Then you take this. Write carbon atomic number 6. Then write general electronic configuration. Then this is ground state configuration. And this is exit state configuration. Ground state is a carbene form. Always ground state configuration of carbon looks like carbene form. Exit state looks like a tetravalent carbon form. So mostly this form we are going to use, not this form. It is a carbene form. Right. In order to attain equal energy bonds, in order to attain equal energy bonds, carbon involved in hybridization. So keep heading hybridization. Carbon involved in hybridization. Right. What is hybridization? Just see. So what is hybridization? Intermixing of atomic orbitals to give equal and similar number of hybrid orbitals is called hybridization. Simply mixing atomic orbitals into hybrid orbitals. Right. Intermixing of atomic orbitals into similar and equal energetic hybrid orbitals. Similar and equal energetic hybrid orbitals. Similar and equal energetic hybrid orbitals are known as hybrid orbitals. And this phenomenon is known as hybrid orbitals, and this phenomenon is known as hybridization. This phenomenon is known as hybridization. So you maintain two columns and write that too. Number of atomic orbitals, number of hybrid orbitals. Okay. Suppose see, I am using one p orbital, one s orbital, and one p orbital I am overlapping, intermixing. So 1 plus 1, how many atomic orbitals are there? 2. One s orbital, one p. It may be any kind. It may be px, py, pz, any one. Then how many you will get? 2 sp. Number of atomic orbitals is equal to number of hybrid orbitals. Second possibility, one s orbital, and here I am using 2 p orbitals. 2 p orbitals means px, py, any two possibilities you can take. Then total becomes 3 sp2. 2 plus 1 is how much? 3. 2 plus 1, 3. First you write down 3. Now 2 p orbitals, 1 s orbital, giving 3 hybrid orbitals. Same way, 1 s orbital plus 3 p orbitals. Then total how much you will get? 4 sp3. Then 1 s orbital, 3 p orbital plus 1 d orbital. What do you expect? Can you expect 5 or no? 5 sp3d or not? 3 p orbital, 1 s orbital and 1 d orbital, sp3d. Total 3, 4, 5. Total 5. Okay. Then here I am using 1 s orbital, 3 p orbital and 2 p d orbital. Then what is your answer? Can I write 6 or not? 6 sp3 d2. So how many atomic orbitals we are combining, that will give same and similar number of hybrid orbitals. So this may be differ. S orbital is differ in their orientation, p orbital also differ in their orientation, but once if they mix together, all are remain same. So once if you mix one s orbital and p orbital, you will get 2 sp, and here 3 sp2, and here 4 sp3. So means all are same. See here, 4 sp3 means 4 sp3 hybrid orbitals, all are same. 4 are same. But here these 4 are not same. 1 s orbital, 3 p orbitals are not same, because this is in px, py, pz direction, and here completely s orbital. So atomic orbitals are differ in their orientation and their energy, but hybrid orbitals are all are remain same. Clear? Right. number of atomic orbitals is equal to number of hybrid orbitals. That is the concept. Okay. So here one formula I will show to calculate hybridization of some selective molecule. First you remember that formula. Hybridization for any reference atom, hybridization is equal to, you remember this, number of sigma bonds plus number of lone pairs. This formula you need to remember. How many lone pairs are present, how many sigma bonds are present, that will give one number. That number is equal to hybridization. Before going some calculations, you remember this. Hybridization is equal to number of sigma bonds plus number of lone pairs. That will give one number. Okay. If that number is 2, see, sum of these two in a given molecule, if it is 2, then what is hybridization? Sp. If that number is 3, then hybridization is what? Sp2. If number is 4, Sp3. If number is 5, sum of sigma bonds, sum of lone pairs, if it is 5, Sp3d, then here it is Sp3d2, like that. Some of these numbers I am saying. Okay. So first one example I will show, just we will calculate later. Around this carbon, how many sigma bonds are present? All are sigmas or not? This is sigma, 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 sigma. Total how many sigmas are there? 4 sigma. Total number of bonds are 4 or not? Then number is what? 4. 4 means the sp3. 4 sigma bonds are present, so hybridization is 4. 4 sp3 is there. Now if I take ethane, here carbon, hydrogen, hydrogen. Okay. So here I am writing carbon with 3 hydrogens, and here also carbon with 3 hydrogens. Around this carbon, how many sigma bonds are present? 4 or not? 3 hydrogens, and this is one more. So total 4. So 4 means what is hybridization? Sp3. And here also what is hybridization? Sp3 only. We need to count even this sigma bond for this carbon. How many hydrogens? 3 hydrogen. 3 hydrogen, 3 sigma, and this sigma bond. Total how many sigma bonds? Total 4. Now this is carbon-carbon double bond. Here I am writing 4 hydrogens with sigma. See, sigma, 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 sigma. This carbon carry how many sigmas? 3 sigma. 3 sigmas means what is hybridization? Sp2. Now it is sp2 carbon. Now this will carry 1, 2, 3. So here also sp2, because they carry 3 sigma bonds. Okay. Suppose if I take carbon-carbon triple bond. Carbon-carbon triple bond. See, this is sigma bond, and what is this? Sigma, sigma. And what about here? Pi bond. How many pi bonds are there? 2 pi. Here how many pi bonds are present? 1 pi bond is present. Okay. So this carbon carry how many sigmas? 2 sigma. What is hybridization? Sp. And this carbon carry 2 sigma. And what is hybridization? Sp. Clear? Suppose if I take carbon, hydrogen, hydrogen, alene. I am taking alene, hydrogen, and here hydrogen. This carbon carries sigma, sigma, sigma. Total how many sigmas? 3 sigmas. So 3 sigmas means what is hybridization? Sp2. And here this carbon, sigma, sigma, sigma. And here also 3, what is hybridization? Sp2. But what about this carbon? This carbon around, only 2 sigma bonds are present or not? Around this carbon only 2 sigma bonds are present, so I can say 2, it is Sp. It is Sp carbon. So don't consider pi bonds in calculation of hybridization. In calculation of hybridization, don't consider pi bonds. Only consider sigma bonds or lone pairs. Only sigma bonds, lone pairs will give the answer. Suppose if I take CH3OH, this is alcohol. Now this carbon carry how many sigma bonds? 3 hydrogens and 1 carbon oxygen sigma bond or not? So total 4. So 4 means what is hybridization? Sp3. And this oxygen carry, see, this is 1 sigma, it is 1 more sigma. Total how many sigmas? Total 2 sigmas. 2 sigmas, 2 lone pair. Total 4. 4 means what is hybridization? Hybridization is sp3, like that. Okay? If any lone pair is present, that lone pair also we need to count. That's why this formula we need to apply. Number of sigma bonds plus number of lone pairs. Right. So just calculate the hybridations of this. Here carbon carbon double bond and here carbon carbon double bond. This is called conjugate olefin. Conjugate olefin. Just write down the hybridations of these particular groups. Primary amine, lone pair. Try to remember some names, even some fragment names also you need to remember. What is conjugation? What is conjugation? Alternative single bond and double bond. Whichever is alternative, anything which is alternative which is helpful to delocalize electron. Don't think that alternative single bond, pi bond is conjugation. Even pi bond and non-bonding also conjugation. It should be alternative. Lone pair separated by single bond and pi bond. Lone pair separated by cation. Anything which is helpful for delocalization of electron is called conjugation. This is under conjugation. Pi bond, single bond, pi bond. This is it under conjugation? No. So here lone pair of electron is present, but this lone pair gets separated by more than one single bond. Single, single, double. Not under conjugation. Now this electrons not involved in delocalization. They won't move. So what is the hybridization of this all? All are sp2 or not? All sp2. Here, this is sp2, sp2. What is this? sp3, and what about oxygen? sp3. Now here, will you calculate sp2, sp3, then here see sp3, and here all sp3. Is it nitrogen hybridization sp3? Yes. 2 nitrogens, 1 sigma, total 3. 3 plus 1 lone pair, 4. Nitrogen hybridization is what? sp3 or sp2? sp3. It is sp3 nitrogen. As P character increases, basicity increases. As S character increases, acidity increases. That's why I am focusing. Remember, don't take that much simple this hybridization. Maximum it will contribute. Even in IR, UV, HNMR, okay? And even in your reagents also, hybridization will play an important role. Which is more acidic, which is less acidic, acidity, basicity, polarity, everything will be decided by hybridization only. If any nitrogen having more p orbitals, whose basicity is very high. Okay? So acidity depends on s orbital, basicity depends on p orbitals. More s character, more acidity, more electronegativity also. If any molecule or any group having more s character, more electronegative, means which is very close to nucleus. Clear? More s character. What is the percentage of s in this one? 25%. S and p, total 4 blocks if you assume. Total 4 blocks is there, 1 s orbital, 3, total 3. So this is S, P, P, and this is P. 25% S character. This you assume as 25%. Clear? So you will understand slowly, but right now I am giving a rough example. Acidity depends on which one? S orbital. Basicity depends on P orbital. That point you remember. Okay, now see this. This is called vinyl alcohol. Remember, what is the hybridization of this carbon? This is sp2, and here also sp2. What about oxygen? Now it is sp2, not sp3. Why? Normally your calculation will give 4 or not? sigma bond, 2 lone pair. What I am saying is don't consider one lone pair on any atom if it is under conjugation. Conjugation helps to delocalize. Is it a localized or delocalized? Delocalized. Delocalized means moving. Localized means not moving. It is a localized lone pair. Lone pair not moving. Is it lone pair moving to one place to other place? No. So this lone pair is called localized lone pair. Localized lone pair should consider in hybridization. If it is delocalizing, see, is this oxygen lone pair is under conjugation? Is this oxygen lone pair under conjugation? Yes. Lone pair sigma bond pi bond. Lone pair pi bond separated by sigma bond. Now this lone pair is under conjugation. If they are under conjugation, don't consider one lone pair. Out of two, one you need to ignore because it is moving. Suppose if there is no conjugation, we need to consider hybridization. See the difference. Is this lone pair conjugate with this pi? No, because lone pair sigma bond, sigma bond. It is not involving in delocalization. That's why sp3. How many lone pairs I am considering in hybridization? 2. But here only 1. What is the reason? It is involved in delocalization. So this oxygen hybridization is what? sp2. So similarly, suppose if I write any chlorine, bromine like this, what is the hybridization of this one? sp2. Here also sp2. What about this? It is also sp2. How many lone pairs involved in delocalization? 1. Remaining 2 are localized. Remaining 2 are localized. Now, if you consider this molecule, what is the hybridization of this carbon? sp2 and here sp2. What about this? sp3. So then automatically it becomes a sp3. How many lone pairs I am considering? 3 lone pairs. Why 3 lone pairs? No conjugation, no delocalization. If conjugation, delocalization is there, then only one lone pair we need to ignore. Otherwise, we can consider. Okay. Suppose see, this is CH3, CH2O minus 1 I am writing. What is the hybridization of this oxygen? sp3. Hybridization is sp3. What is minus 1 indicates? See, already one lone pair is there or not? Already 2 lone pairs are there on oxygen. And see here one hydrogen is there. So hydrogen is removing in terms of H plus. So if this electron, if you add on this electron, then this oxygen become minus 1. Means initially this electron belongs to which one? Hydrogen. That electron we are adding here. If you add this 2, now this 2 electron belongs to oxygen. Initially this is only one electron belongs to oxygen. This is belongs to hydrogen. So that's why I am writing minus 1. If I write minus 1, remember one lone pair. Anywhere. One extra electron converted to lone pair. That is the meaning. Already 2 is there, 1 extra. Total 3. 3 lone pairs. Anyone is delocalizing? No. No one is delocalizing. So that's why 3 lone pairs, 1 sigma. 1, 2, 3. And this is 4. 4 means sp3. This 2 also sp3. Okay. So will you consider this? CH2CO minus. What is the hybridization of oxygen? What about hybridization of this 2? sp2, sp2. What about here? Is it sp2 or sp3? sp2 only. Why? Negative charge is delocalizing. Negative charge is delocalizing. That's why we need to write like this. So what is the hybridization of nitrogen in this one? It is sp2. So similar way we need to write one more example. Here nitrogen I am writing. So what is the hybridization? Nitrogen hybridization is sp3. It is not involving in conjugation. Right. First you write molecules fastly. First you write molecules very fastly. After writing molecule, try to write without watching. So that will give practice for you. Wherever you are unable to attempt, that point you focus. Wherever you are writing very fastly, you can ignore it. You can guess like this. sp2, sp2, all are sp2, sp2, sp2. So here just you focus here. 2 lone pair, that's no conjugation, sp3, like that. You need to think and write. So don't copy. Every time don't copy organic molecules. Try to analyze it. Try to work out. Here 2 chlorines I am giving. What is the hybridization of 2 chlorines? Vicinal dichloride. What is the hybridization of these two? Is it sp3? sp3 is also sp3. Why? There is no conjugation. Conjugation is present or absent. No more conjugations. So this is called glycol. What is the hybridization of oxygens? sp3. All are sp3. Just go through it. CH double bond CH. Here chlorine and chlorine. What about this? sp2. Here also sp2. Why? See, double bond conjugate to lone pair. Out of 3 lone pairs, 1 lone pair involved in delocalization. Ignore 1 lone pair. If conjugation is there, blindly attempt the same concept. Okay? So even if I take one ether, this is ether I am saying. What is the hybridization of oxygen? Is it sp3 or not? What about remaining 2 carbons? These 2 carbons hybridization, sp2. Now here if I write this, oxygen hybridization. Oxygen hybridization is sp2. What about these 2? sp2, it is sp3. sp2, 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 sp3. Here how many lone pairs involved in delocalization? Only 1. Okay? So, if any heteroatom adjacent, if any positive charge is present, remember, this is heteroatom, here positive charge is present, lone pair. What is the hybridization of this carbon? Here sp3. Then what about hybridization of this one? sp2. Because only sigma bonds are there. What is plus indicates? What is plus indicates? Cation. Cation means there is no electron. Means there is empty cavity, empty orbital. Now this lone pair involved in delocalization. It is involved in delocalization. So can I ignore 1 lone pair? Yes, ignore this. Then consider sigma, sigma, lone pair. Total 3. 3 means sp2. When positive charge is present adjacent to any heteroatom having lone pair, then lone pair involved in delocalization. Clear? Suppose if negative charge is present, it is not like that. They never involve in delocalization because negative means extra electrons. Positive means no electron. Clear? First you write molecules fastly. Whichever is easy, that you just leave it. Whichever you are confusing, that you write down first. So what is the requirement for delocalization? Planarity. If it is under planarity, then only electrons will undergo delocalization. If there is no planarity, it is not possible to delocalize. CH3O, and here I am writing minus your lone pair. What is the hybridization of oxygen? sp3, and carbon is also sp3. Negative means one lone pair. Suppose carbon carry 3 hydrogens and one negative charge. Negative charge means -1. Then what is hybridization? sp3, carbanion. Suppose if it is a carbocation. Carbocation means carbon bearing positive charge. Only 3 sigma bonds are present, sp2. Suppose if it is a free radical. Free radical means how many electrons? Only one non-bonding electron. It is one non-bonding electron. So then what is hybridization? sp2. 1, 2, 3. Only sigma bonds, don't consider radical. Don't consider radical in calculation of hybridization. See, this is CH2 dot. What is hybridization of this lone pair? Lone pair hybridization is sp3. And what about this carbon? This is sp2. Radical nothing but non-bonding electron. One electron is there, it is not involving in bonding. That's it. Right. Slowly we are entering into charges. Remember, if any positive charge is there, that is a disturbing factor. If any negative charge is there with conjugation, that is also get disturbed. If negative charge without conjugation, we need to consider. Negative charge is there, but it is not involving in delocalization. Now we am considering. Here also I am considering, because no delocalization. Negative lone pair never involve in delocalization. Negative lone pair never involve in delocalization. Negative positive involve in delocalization. Negative positive. Almost all looks like this. Here if I write negative, here if I write positive, then both involve in delocalization. This is singlet carbon, triplet carbon, singlet nitrine, triplet nitrine. What is the hybridization of that carbon? Is this carbon having 2 sigma bonds? Carbon having 2 sigma bonds or not? Carbon with hydrogen, 2 sigma bonds are there. One lone pair. 2 sigma bonds, one lone pair. So now it is sp2, total 3. Now this carbon having 2 sigma bonds, but 2 electrons not lone pair. They are independent electrons. They are present in a different orbitals. So then what is hybridization? This is sp. It is not sp2. Singlet carbon sp2, triplet carbon is sp. And here also same. 1, 2, 3. Nitrogen. What is the hybridization of nitrogen? sp2. Here hybridization of nitrogen is sp. Now this is formaldehyde. What is the hybridization of oxygen in formaldehyde? Is it sp2 or not? What about carbon? sp2. It is also sp2 or not? Here one sigma bond and how many lone pair? 2 lone pair. 2 lone pair not involving in delocalization. That's why I am considering 2 lone pairs. 3. 3 means what? sp2. Clear? So can I apply for acetaldehyde? This is acetaldehyde. Lone pair, lone pair. Acetaldehyde. What is the hybridization of this carbon? It is sp2. And what about here? sp2. Now what is the common thing you observe between these 3? So this is ketone. Acetaldehyde, acetaldehyde, methanaldehyde. This is called propanone, ketone. What about this? It is sp2. And what about this one? sp2. Is it common or not? C double bond Y is called carbonyl unit. Carbonyl unit is common for aldehyde, formaldehyde. What is one more? Ketone. So always this oxygen, how many lone pairs are present? 2 lone pair. Out of 2 lone pair, how many are delocalizing? How many are delocalizing? Not even one delocalizing. So if they are not delocalizing, consider 1 lone pair, 2 lone pair, 1 sigma bond. Total 3, number 3. Number 3 means what is it? sp2. Be careful from here onwards, especially oxygen, target oxygen, nitrogen, chlorine. Because most of the functional groups carry, organic functional groups carry these 3. Carboxylic acids, esters, acid halides, amides, nitriles, everywhere. Oxygen, nitrogen or halogen. Only these 3 will be there. So that's why focus whether lone pair is delocalizing or not. If they carry 3 lone pair, if one is delocalizing, consider 2. If they carry 2 lone pair, one is delocalizing, consider 1. Clear? Right. See, here I am writing C double bond O, here lone pair and here lone pair, here positive charge. This is called acyl cation, acylation, Ferrell-Craft acylation. You know, Ferrell-Craft acylation. What is the hybridization of that oxygen? And what is the hybridization of carbon? Carbon is what? sp. What about nitrogen? Can I consider 1 lone pair or 2 lone pair? See, lone pair adjacent carbocation is present, so they undergo delocalization, 1 lone pair. And here positive charge. This lone pair involved in delocalization with this positive. So you will get carbon oxygen triple bond. So this is sp, it is also only 1 sigma, 1 lone pair. So it is also sp. See, same group if I write here, see. In place of CH3, I removed CH3, I am introducing positive or not. On this carbon if I write positive, this lone pair involved in delocalization. Clear? Initially it is sp2. Initially it is sp2. Right now it becomes sp, which indicates that this lone pair involved in delocalization with this empty orbital of carbon. So we can write this acyl cation like this even. Now cation is stabilized by non-bonding electron. CH3 C double bond OH acid, and here I am writing anion, there I am writing ester, ester acid halide, amide, this is NH2, then amide anion NH minus, CH3 double bond NH N minus 2, then anhydrate. All functional groups I am writing. All organic functional groups, you are in a position to identify their hybridization without any confusion. If I write positive charge, negative charge, radical, with lone pair, without lone pair, anything, you are in a position to identify their hybridization, so that spectroscopy will be very easy for you if you know this concept. It will helpful in spectroscopy, not spectrometry. It won't helpful in mass spectrometry. Mass only breaking, blindly it is breaking. But especially in IR and HNMR, this plays an important role. If electron negativity increases, withdrawing capacity also increases. Electron density decreases, chemical shift value increases. So it is linked with HNMR, with chemical shift value. This is double bond O minus, and this is plus. This is a tertiary amine. First, identify whether lone pair involving in delocalization or not. Here this is lone pair, here positive charge, this is CH3, and here one more CH3. This is quaternary. Stevens rearrangement, Somlet-Hauser, or belongs to quaternary. Can you guess? Only conjugation can help. If you identify conjugation clearly, your answer is very easy. If you are unable to identify, it is one of the toughest area to attempt. Conjugation is the most important factor. See this. Listen. Everyone listen. So what is the hybridization of this? What is the hybridization of this one? sp2 or not? And what about here? It is sp2, not sp3. Because see, so if you observe clearly, this lone pair involving in delocalization. This is also involved in delocalization like this. That's why one lone pair we can ignore. Clear? Now in this one, see. What is hybridization? Carbon, what is hybridization? sp2 only, everywhere C double bond O, wherever it comes. C double bond O, carbon is sp2. No need to work out. Now here, sp2, and here, sp2, this one. sp2, here. sp3, sp3. Carbon, there is no problem at all if it is a tetravalent with hydrogens. Here, sp3, here, sp2 chlorine, sp2. One lone pair I am ignoring. Now this one. sp2. One lone pair is there. That lone pair involved in delocalization like this. What about oxygen? sp2. Here, on this nitrogen, how many lone pairs are there? 2 or 1? 2 lone pair. One is its own, one is extra. Minus 1 means 1 extra lone pair. Minus 2 means 2 extra lone pair. Minus 3 means 3 extra lone pair. Like that. Here what is hybridization? sp2. Here sp2 only. This and the same. How many lone pairs are present? 2 lone pairs, in which one lone pair involved in delocalization. And here sp2 only still. How many lone pairs on this nitrogen? Total 3, one is involved in delocalization. Here it is always sp2, sp2, sp2. What about this? sp2. Here nitrogen sp2, oxygen, all are sp2. Can you work out this? What about nitrile? This is sp. Here this is called nitrile, cyanide. Cyanide. Nitrogen 1, 2. What is hybridization? sp. One lone pair, one sigma bond. Now here what is the hybridization of this oxygen? Is it sp2 or not? Yes. 3 lone pairs are there, one is involved in delocalization. What about this one? Is it sp2? Yes. It is also sp2, oxygen also sp2. Whichever lone pair is delocalizing, ignore it. One lone pair you can ignore out of available. Clear? Now this one. Here sp3 or sp2? sp2. Then here this one. This is sp2. And here one, two, three. What is hybridization? sp2. This lone pair not involving in delocalization. This one. Only this lone pair can involve in delocalization. What about nitrogen? sp2. Sigma bond, sigma bond, sigma bond. 3 sigma bonds. Now benzene. See, this carbon carry how many sigma bonds? 3. 1 sigma, sigma, and here hydrogen. So all are sp2. Now benzene on are sp2. What about this methyl? sp3. Chlorine. Now it is sp2. It is not under simple chlorine. It is conjugate to benzene. Ignore one lone pair. Chlorobenzene, chlorine hybridization is sp2. Right. This one sp3. How many lone pairs? No lone pair. sp3, sp3, sp3. Here lone pair conjugate to positive. It can involve in conjugation. So now what is hybridization? sp2. Now this one sp3. All sigma bonds are there around nitrogen. There is no lone pair on this nitrogen. All are sigma bonds. So I can say 4 sigma bonds sp3. Suppose if I take phenol, what is oxygen hybridization? Is it sp2 or not? sp2. Then what about phenoxidine? It is also sp2 only, no change at all. Phenoxide and phenol both are same. Now if I write any carboxylic acid, what is hybridization of two oxygens in carboxylic acid, benzoic acid? Here one lone pair delocalizing, here two lone pairs are available. So this is sp2, it is also sp2. Okay. Even if you take any amide, your answer is remain same. This is amide. This is salicylic acid. This is C double bond O Cl, and here one more chlorine. What is the hybridization of two chlorines in this molecule? This chlorine hybridization is sp2, but what about here? It is sp3. It is not under conjugation. Here this is sp2. Here sp2 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 sp2, all are sp2. This is called cyclopropenyl cation, cyclopropenyl cation, cyclopropenyl anion, cyclopropenyl radical, cyclobutadiene, here dication, here dianion, cyclobutadianion. Now here I am writing cation and anion. 4 cations I am writing. Now this is most known molecule, cyclopentadienyl anion. So this is cation, and 6-membered well-known benzene. If I remove these two and if I write 2 positive charge, you will get this 2 negative, and this is zone membered ring plus tropylium. Zone member ring. Give the hybridations of this. If you know this, it is helpful for concept of aromaticity. What is the common requirement for aromaticity? Either sp2 carbon or sp carbon, but not sp3. If it is sp3, non-aromatic. If it is sp2 or sp, may show aromatic or anti-aromatic. So that's why hybridization will play a biggest role in organic chemistry, especially in case of concept of aromaticity and reagents, in reagents and spectra. Without any mistake, you need to write hybridations of individual element. What is hybridization in this? All sp2, all sp2, all sp2, here also sp2, 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 all are sp2. Okay, here see, is this negative under conjugation or not? That's why ignore it. Here also under conjugation if it is delocalized this side. So if any negative charge is under conjugation, ignore negative charge. Now here sp2, here also all sp2, 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 sp2. All are sp2 in this all examples. It may show either aromatic or anti-aromatic. First condition is they should carry sp or sp2 hybridization but not sp3 for showing aromatic or anti-aromatic. So this is 7-membered ring with anion and I am writing 8-membered ring. 8-membered ring cyclooctatetraene. Cyclooctatetraene adopts a tub-shaped structure. So these double bonds not involved in delocalization, away from planarity. Even though they all are away from planarity, but always sp2 because it is tub-shaped molecule. This double bond almost all equal to a normal double bond, simple double bond. Okay, then you can take any 8-membered ring with 2 positive charges. Here positive, here positive. Cyclooctatrienyl dication. Then cyclooctatrienyl dianion. So what is hybridization on this all carbons? This is sp2. Here also all are sp2. All sp2. So these two are aromatic. These two are aromatic because how many electrons are delocalizing? 6 electrons. This is non-aromatic, non-planar, non-aromatic. First thing for aromaticity is planarity. Is it planar? No. If any positive charge, negative charge is there, irrespective of the ring size, mostly they are planar. There is no positive or negative charge, it is non-planar. What is the meaning of planar? Flat. What is the structure of benzene? Flat structure like this. Looks like a paper. Flat structure. If you leave paper, how it will stand on surface? With a stand like this. Suppose it is a surface. If you leave one paper with your hand, leave that paper, it will float and it will stand like this. Possible? Out of 100%, how much possibility is there? Even 1%? Not even 1%. Less than 1%. Possibility is there, but maximum not possible. So maximum they will fall like this. Even if you leave like this, it will fall like this. Even if you leave like this, it will fall like this. Okay, so all constant atoms in that molecule is going to touch surface of a plane. That is called planarity. All are planar. If charge is there, planar. Suppose if charge is not there, some molecule due to their ring size, they may be non-planar. It is a tub-shaped molecule, remember. Tub-shape. 8-membered ring is a tub-shaped molecule showing non-planarity. Non-planar. So don't say anti-aromatic, don't say aromatic for this. But follow Huckel's rule. 4n pi Huckel's rule it will follow, but it is not a anti-aromatic. It is non-aromatic. This molecule is very, very important. If you remove 2 electrons, aromatic. If you add 2 electrons, aromatic. But if you leave it, non-aromatic. It is not anti-aromatic. This is anti-aromatic, anti-aromatic, aromatic. So maximum they are aromatic or anti-aromatic by following 4n plus 2, 4n pi electron rule. But only this one is non-aromatic due to away from planarity. So this molecule is known one for you. This is called THF. Tetrahydrofuran. What is the hybridization of oxygen and THF? What is hybridization? sp3. Suppose if I write any double bond over here, what is hybridization? sp2. If I write 2 double bonds around this oxygen, Then what is hybridization? It is sp2. What is this molecule name? Furan. Right? Now, what is the hybridization of this oxygen in this molecule? Oxygen. Oxygen hybridization is sp3, not under conjugation. There is no conjugation in this one. Okay? So, can I write this molecule? What is the name of this molecule? This is pyrrole. Pyrrole, furan, and if I write sulfur, pyrrole, furan, and this is thiophene. And here one lone pair is there. Now, say the hybridization of nitrogen in this one. Hybridization of nitrogen is sp2. Here sulfur is sp2. How many lone pairs are delocalized here? One lone pair. One lone pair is localized, other is delocalized. Inside, if I write any lone pair, that is delocalizing inside of the ring. If I write lone pair outside, it is not delocalizing. It is outside of the ring. What is the meaning of localized and delocalized? Delocalized means moving. Fan is delocalizing when I switch on. Fan delocalized when I switch on. Fan is localized when I switch off. Localized means it is not moving. It is not moving in a clockwise or anti-clockwise manner. Simply, it is standing. Delocalization means unnecessarily delocalizing. Unnecessarily moving. You are not sitting at one place. Suppose in your house, if any holiday is there, so in your house, in your room, you will keep on delocalizing. Outside, inside. Okay, then you will fight with your mother, father, child, everyone. Because instability. Suppose if you take age-old people, 80 years, 90 years, what happens? Localization starts. They are unable to move. Then what happens? If they are unable to move, they keep on localized. At one place, they will settle down. Means when energy is there, what happens? Localization increases. When energy down, slowly you become a localized. Here also same. One lone pair is delocalizing, other lone pair is localized. If it is localized, then only that lone pair available for acids. Then only we will consider the basicity. Basicity depends upon localized lone pair only. Okay? If it is continuously running, we should not consider, ignore it. Basicity explained based on localized lone pair. If any lone pair is localized, basicity increases. If there is no localized lone pair, that molecule is highly inert. So is it a basic in nature? Is it basic in nature? No. Why? Only one lone pair is there, but that lone pair is delocalizing. That's why pyrrole is least basic. So what is the common hybridization between these three? See, pyrrole, furan, and thiophene. This is thiophene. Pyrrole, furan, thiophene. What is the common hybridization? sp2. These all are aromatic because they have delocalized pi electrons. Electron-rich heterocycles they are. As compared to benzene, they have more electron density. Benzene having less electron density as compared to pyrrole, furan, and thiophene. Clear? Slowly you will learn in concept of aromaticity. Right now your target is how to calculate hybridizations of individual atoms. What is this molecule name? Pyridine. Pyridine. Is it localized or delocalized? Localized. A lone pair is available for acids, but this lone pair is not available for acids. So I can say pyridine is more basic than pyrrole. This is more basic as compared to this one. Because a lone pair is present or not. Lone pair is there, but it is delocalizing. But here lone pair is present, it is localized. So this is more basic as compared to pyrrole. Now what is this? Indole, quinoline, isoquinoline, and this is called enamine. You know star enamine reaction or name reaction. That is with this. Alpha comma beta. With respect to nitrogen, it is alpha carbon, and this is beta. Alpha comma beta unsaturated amines are called enamine. En means double bond. En plus amine, enamine. Adding any electrophile on this enamine is called star enamine reaction. Adding any electrophile on this molecule is star enamine. What is this? Pyridine, remember. Pyridine. And what is this? Indole. Here, quinoline. And this is isoquinoline. All having lone pairs. Lone pairs are localized. Now what is the hybridization of these all skeletons? All are sp2. Everywhere nitrogen sp2 only. sp2, sp2, here also sp2, sp2. All nitrogens sp2. Even this also sp2. Why it is sp2? This lone pair is delocalizing on this, and this will be migrated up. It is a delocalized lone pair, so I can say it is sp2. So all nitrogens are sp2. Now what about last molecule? Oxygens. Two oxygens. Two oxygens having sp3 or not? sp3, and here also sp3. What about these two carbons? sp3. And what about this? It is also sp3. Is it carbon? Carbon or not? Yes. So it is sp3. So what is final conclusion? How to determine hybridization? Number of sigma bonds plus localized lone pairs. Suppose if any molecule having 10 lone pairs, only one lone pair involved in delocalization if it is under conjugation. All will not involve. Only one lone pair you can ignore. If they carry two lone pair, one involved in delocalization. If conjugation is there. If conjugation is not there, we can include them. Clear? So now I will give one question. Just try to write the examples in that one. Give a set of molecules having one carbon with sp3 hybridization. So write the answers over here. Give a set of molecules in which how many carbons are present? One. Only one carbon is there. Definitely that carbon should be sp3. They should not carry more than one carbon. They may carry other elements. That is okay. They may carry chlorine. They may carry hydrogen, oxygen, nitrogen, sulfur. You take any other elements. But if you write a molecule, I won't see more than one carbon. Can you give an example? Methane. Methane is the best example. Any other? Any other example? Chloroform. CHCl3. Possible? Okay. Carbon tetrachloride. CCl4. Then DCM. What is DCM? Dichloromethane. Dichloromethane. Then can I take methanol? How many carbons are there in this one? Only one. And can I take methyl chloride? Can I take methylamine? Okay. So can I take methyl carbanion or not? That is creativity. Like that, creativity is required. Generally, only one methane will come in your mind, then it will blink. You will think. You can also write many examples. I can write with sulfur, with selenium, arsenic. You take any one, but only one carbon. Other elements should be any one. I take a mixed halogens here, bromoform, iodoform, any one I can take. But carbon is only one. All single bonds are required. That is the question. That is creativity. If you know this one, spectroscopy is very easy for you. You can create a unknown sample will be given in your laboratory. Your guide will give an unknown sample. They will ask, determine the structure. If you know mechanism, spectra, your PhD is over. Only 2 points, mechanism and spectra. If you are very strong in mechanisms and if you are very strong in spectroscopy, your PhD is very easy. Once sample is isolated, you can write the complete history of that sample. You need to determine the mechanism. You need to write the complete spectral evidence. You need to write the mechanism. So breakage process will be there, mass spectral breakage. You can determine the structure, HNMR evidence, IR evidence, over. That is the advantage of basics and spectra and mechanism. You should be strong in mechanisms. Okay, you need to practice once and twice mechanisms. Once if you practice once and twice, automatically it will be there in your mind. And how to remember mechanisms, I will show some selected area, how to remember mechanism without any confusion and without any fear. Generally, whenever if you want to write mechanism, your hand will not move. Okay, you will stop at one place. Once if you stop, definitely you people will do mistake. Next step is mistake only if you stop. So for that, what is the process? I will explain. But thing is, first you need to know basics clearly. If you are very strong in basics, no need to think about mechanisms. If you are very strong in mechanisms, no need to think about name reactions. Suppose carbocation is there. So think about some name reactions of carbocation. Name reactions of carbocation. Pinacol, pinacolone rearrangement. Dinone, phenol rearrangement. Tifeno, demgeno rearrangement. Okay? Carbene rearrangement. Untested rearrangement. Wolff rearrangement. Like that, many you can write. If you know mechanisms clearly, based on that, you need to write the named reactions and rearrangements. Generally, what you people, you will do? Generally, you will learn named reactions, then you want to remember mechanism. That is a wrong idea. In your theoretical papers, in your PG, in your degree, they will explain like that only. That is a process actually. But that is not a correct way to remember reactions and mechanisms. First thing, focus intermediate. How to prepare that intermediate? What is the process to prepare that intermediate? What is the answer? Over. Name reaction is over. Suppose aldol condensation. Intermediate is carbanion. I can write. Take a base, generate a carbanion, attack another one, condensation, beta hydroxyaldehyde. Over. No need to by heart any name reaction, no need to by heart any rearrangement. If you know intermediates clearly, if you have a grip on mechanisms clearly, automatically names will come. Only few points, key points you need to remember. Pinacol to pinacolone, pinacol-pinacolone rearrangement. Unstable carbocation to stable carbocation. Wagner-Merwin rearrangement, like that. Clear? Right. Almost all same question, but only thing is I want to write sp2. Carbene. Next. So carbene is correct. Is it singlet or triplet? singlet carbene, right? So can I take C double bond OH, carboxylic acid, formic acid? Okay. So can I take ester? Otherwise we can take formyl chloride, formamide. Okay. So formamide, formyl chloride, and even formaldehyde, etc. We can write like this. Only one carbon is required. So you take this with sp. Give a set of molecule with sp hybridization. They carry only one carbon, and that too sp. You can take other elements but not carbon. Best example, triplet carbene or not? Triplet carbene, then carbon dioxide, CO2. Okay. So can I write allene? No. Allene carry 3 carbons. Central carbon carry sp, but the other 2 carbons carry sp2. Carbon disulfide. Okay. Then can I take hydrogen cyanide? So what is the hybridization of this carbon? sp, like that. So that is end of hybridization to determine for individual organic functional group. Okay. So in your next class we'll see how overlaps are helps to determine the hybridization. Okay. Then we'll see some selective questions on hybridization. Okay. We'll stop here. We'll continue tomorrow. Tomorrow same time.